Hello, I'm Grace Stout, and this is my Kinetics Take-Home Exam 2, problems 3 and 4. So I guess I'll just jump right in. So problem 3 here, part A, calculate the effective diffusion coefficient. This was pretty much like one of our homework problems from the last homework. We got like the pore radius, and then we plugged it into this equation for the Newton diffusivity, and then we could neglect DAM because the pore diameter was very small, so that was one of the assumptions. And then that made like the total diffusivity just basically equal to the Newton diffusivity as seen here. And then from there we were able to plug that into this equation and then get our effective diffusion coefficient. Yeah, so pretty plug and chug for that. And that was for N-butane. And then the reaction was diffusion limited in these conditions because when we calculated eta, it was less than 0.5. So eta is the ratio of the observed rate to the rate without gradients. So since it was low, that means the reaction is not limited by gradients, so it has to be limited by diffusion. Here's my little eta calculations. This is like straight from the notes, just like pretty plug and chug. And then once I got phi, just plug that into Excel to get like my tanh stuff. Anyways, and then for this part C, observed rate constant is just going to be AV over particle, oh my gosh, density. Again, super plug and chug. The density is just epsilon over the volume of the particle, which is like sphere. And then got that answer. And then I guess we'll move right on to question 4, which is the fun one. Okay, so this is irreversible reaction, yada yada. Let's go over to my VMware for part A to achieve 50% conversion if it's isothermal. Oh, it's not letting me switch. Just a sec. Hello? Okay, there we go. Okay, so if it's isothermal, here I have T is going to be that 830 Celsius plus 273 to get to Kelvin. I have my rate. I have like my K calculation. Pretty explanatory. I assumed the pressure was 1 atmosphere, so it was 101.325 kilopascals, which I used in my total concentration calculation here. And then I did everything in moles per second, which is why sometimes I'm dividing by 3,600. I put everything in like moles, liters, and seconds. This stuff will come in later. And here are my mole balances. It's for a PFR, so it's like D flow rate dV is going to be the reaction rate, super simple stoichiometry here, and then I do F total, and then my mole fractions, and then my concentrations here, and then here are my initial conditions. Since they're in moles per second, it's like 1/3 each. And then, yeah, let's see. So I'll show you, I guess, let me jot down what the actual answer is so I can change it back. But if I change this to like well, let's actually just make it 0.405, and then let's make this like 134.405, and then we'll solve it, and then we'll see that the conversion of toluene, I think it's what it was, is 0.347. But then if I change it back to 234.405, then boom, my conversion is 0.5. Oh. So that was the goal for part 1. Now for part 2, without doing any calculations, if it was adiabatic, would it go up, stay the same, or go down? So the heat of reaction is less than 0, so it's exothermic, but it's irreversible. So at high temperatures, Le Chat's does not apply since there's no reverse reaction. It's not like at a high temperature it can like push the reaction back the other way. So at a higher temperature, it's just going to lead to a higher reaction rate because R, like as T increases in this, R also increases. So reaction rate increases, and then fractional conversion will also go up with that. Moving right along. Here we go. Now it's running adiabatically, and we want to know the volume and outlet temperature to run at this. So now we need to include this like del T adiabatic. This was from like one of our class activities a while ago, I think. So this is just like our equation for that, and then our T out is now going to be like our T plus this like fudge factor, I guess, for T. And then also with this, we have to add this into our K for that because T is in that, and then also we need to add it to where's this? I guess I could have just made it T out instead of like messing around with this, but I just thought of that now. And then let's make sure, okay, and then I will run it, see what I get. Okay, so if I go down here, I see that X is 0.95. Since I only want a 50% conversion, I can drop that final volume. I have the value here. So the actual number I got was 98.763, and I solved that, and then boom, I get the conversion is 0.5, and then I also get, I think I was looking for T out. T out is 1192.6, and yeah, that's what I have there and there. Okay, perfect. Moving on to the last part, part D. So this one was kind of crazy because it gave us the ratio of U to D. But Cole found like this like crazy video of this lady like doing the like pretty much the same problem. And basically how she did it was she did it like we know U over D, we can solve for U here, and then she did it in terms of U little a instead of like area, where little a is area over volume, which for this, since it's a cylindrical exchanger, it's going to be 4 over D. So then we can sub that in, and then sub in this U value, boom, and then we can get the D's to cancel, and then we get 40 is like our UA value. So if I go back here, also in this video, here's like my UA, and again, I divided by 3600 because I'm doing it in terms of seconds and I have to move really quick because I'm almost out of time. But also this DTDV was a part of um, the video that Cole found, crazy random video that he found. There we go. Okay, so I got rid of that. Okay, and then I think we're leaving V the same. I need to have an initial condition for T down here, and I also need to block out this T. Hopefully it runs. Okay, and it wants to know, yes, okay, Erin. It wants to know the conversion of T again, which is 0.33, and then the other thing I wanted to know was T, solve for here, 101,124.8, and then if we pop back right here, we have those values right there. Okay, I'm gonna stop because I'm almost out of time, but I hope this was good.